This talk is called NP Complete Problems and Physics. There's, I suppose, a quantum computer saying that some SAT instance is satisfiable. I do a lot of lab tours these days, so this is not exactly what they look like. Okay, but when you do a Google image search, it's what comes up. Okay, so let me start with why I'm here. I've known Steve for, I guess, 20 years or so. I've loved and admired him as much as the next complexity theorist. But, when I was invited to speak here, my first answer was, well, I'm honored, but I can't, because, this is the last the last week of teaching at UT Austin. I have to teach my class. I have to help take care of the kids. I just, I can't do it. And so then I told Donna, who is my wife, and Henry's advisor, who you just heard about, and she is constantly imploring me to do less travel and spend more time helping at home. So I was sure that she would be proud of me that I said no even to the Cook conference. But she surprised me by saying no. Find someone to cover your class. I'll watch the kids. This one you must go to. So I said, why? And she said, well, because it's Steve Cook. And because 50 years ago, he was an assistant professor and was pursuing not what was fashionable at the time or what would get him tenure, but what complexity theory and P and NP, even when much of the world wasn't yet ready for it, or ready to understand it, and it's because of that this field exists today. So anyway, you can see that I'm here. Yeah. Okay. So let me tell you what this talk will not be about. So first of all, it's not going to be a survey of NP hard problems that happen to involve physics. I mean, there are many such problems, interesting ones, but that's just because there are NP hard problems in pretty much every field. In biology, economics, art history, gender studies. Well, I don't know about every field, but you understand what I'm saying, okay? NP hardness is ubiquitous. The other thing that I'm not going to focus on is the quantum version of NP completeness, which is called QMA completeness. QMA being quantum Merlin-Arthur. Okay, so there is a seminal result from 20 years ago we call the quantum Cook-Levin theorem, although it was proved by Kitaev. The original Cook-Levin theorem is, some level beyond seminal, but this, merely seminal result, I guess, which says that the quantum, a natural quantum generalization of KSAT is complete for QMA, or strictly speaking, for the promise QMA. Okay, and the interesting part is that it doesn't work to ask for a tableau of a whole computation the way the original Cook-Levin theorem does. You can't check that locally. So what you instead ask for is something called a history state, which is a superposition that contains for every time step t, t together with the state of the quantum computer at the tth time step. And then that thing can be checked by a bunch of, local measurements, which are the analogs of clauses here. Okay, so there's a whole beautiful theory of that, but that's also not what I'm going to focus on today. What I'm going to focus on is, I think there's a single scientific question that sort of maximally ties together all the different things that I've cared about in my career, and it's the following. Is there any physical means to solve NP complete problems or arbitrary NP problems in polynomial time? Okay, that's just very basic. Very, I presume that if you're here, this is a question that would interest you. And what's amazing about this question to me is that it includes at least 5 different things as components. Each of which, any of which you could spend a lifetime on by itself. Okay, first of all, obviously, it includes the original P versus NP question. Okay, then it includes the question of, do analog continuous processes in nature somehow just naturally solve NP-complete problems, even if digital computers can't? Of course, there have been decades of speculation about that, and I'll say more about that later. Then, thirdly, of course, it includes, can quantum computers efficiently solve NP-complete problems? Is NP contained in BQP? BQP being bounded error quantum polynomial time. So just the quantum generalization of P, or really of BPP. Okay, and then fourthly, well, we should also ask the question, is BQP realizable in our universe? Or more prosaically, can we actually build scalable quantum computers and have them work? We'll say something about that. And then fifthly, it includes the question, is there anything that is physically realizable that goes even beyond BQP? Okay, is quantum computing sort of the end of the line, or will there be some future revolution in physics that would take us even beyond that? Okay, so I'm going to basically proceed through all 5 of these questions in this talk. But let me first discuss, why is NP completeness specifically relevant to this question? Who cares about completeness? Well, if it had not been for NP completeness, then it could have been a priori that there would just be 1,000 disconnected little villages of computational hardness here and there. And then, if we were going to ask a question about physics, what are the limits of what the physical universe lets us efficiently compute? Well, it would just degenerate into 1,000 little sub-questions, with no particular reason for focusing on one rather than another. Okay, but it's because of NP completeness that we know that, yes, there are a bunch of these villages, but there's also, a sprawling metropolis of computational hardness. That's Toronto. So there's this, clear target that it makes sense to really focus on. And I'm constantly talking to people in other fields, who look at, let's say, Shor's algorithm, which is the thing that solves factoring in quantum polynomial time, and to them, that is morally sort of just as amazing as solving NP-complete problems. They don't really perceive any difference between the two. And so I'm constantly having to explain to them that while, yes, Shor's algorithm is amazing, there is an enormous qualitative gap here, right? The metropolis of hardness has not been breached, okay? Okay, so my first question was, does P equal NP? Well, if there's any conference where I don't have to belabor this question, I think it's this one. If you haven't heard enough about it and you want to know more, you could read, for example, Steve's beautiful description of it for the Clay prize problems, which is 12 pages long. Or if you're a masochist, you could read my survey from 2 years ago, which is 122 pages. By the way, when in citation indices, they missed this text symbol for the equal with question mark. So the paper is just called P equals NP by Scott Aaronson. Okay, so for the record, I like to say that for me, I believe they're not equal. I believe that if we were physicists, we would have just declared that a law of nature and collected Nobel prizes for it. And of course, if later the law were to be refuted, we could just collect more Nobel prizes for its overthrow. Okay, but we come from math, so we call it a conjecture. Okay, so, okay, now the second question, is, if you remember during Mike Sipser's talk, Jack Edmonds, raised this point that, well, it seems like in real life we could just say P is not equal to NP and be done with it. Okay, well now one problem with that is that I'm constantly talking to physicists who, they say, oh, well in real life P equals NP. Because, systems just find their lowest energy states. They just get into their ground state, and stay there. And, but getting into the ground state is an NP hard problem, and yet nature does it. So, it's only you theorists who believe P is not equal to NP. Right? So, people have conflicting intuitions about what's true in real life. But, it's worth at least examining this. So there's many ideas along these lines. One of my favorites is the soap bubble computer. Okay, so this is the following approach to solving an NP hard problem. You just take two glass plates, you put some pegs between them, however you like. You dip it into a tub of soapy water. You take it out. You let the soap bubbles relax, into their kind of lowest energy state. And heuristically and empirically, what you tend to see happen is that the bubbles relax to the minimum Steiner tree. Okay, and of course this is an NP hard problem, even in the plane. Okay, and yet nature just seems to do it. So what gives? What's going on with that? People were debating this online some 15 years ago. So I actually built it and tried it out. This is as far as I've gotten into experimental physics, by the way. And that you should try it. With 3 or 4 pegs, typically it does find a minimum Steiner tree. On the other hand, 5 pegs, 6 pegs. Yeah, it starts getting stuck in local optima sometime. That's right. And, it's not like I tried every possible brand of soap, but, I think, I have some indications that nature is not solving, that we're not going to be breaking RSA this way anytime soon, let's say. Right. And, to me, this is, just what one should have expected. I mean, if you had some rock in a crevice on a mountainside, then yes, it could reach a state of lower potential energy by rolling up first and then rolling down. But, it's rarely observed to do that. Okay? So, yes, the systems, nature can get stuck in local optima, right? And it seems like, this intuition that they're just going to be in their ground states is an artifact of looking at what we would call easy instances. Okay, that may sound banal, but you constantly see claims put forward in various fields that sort of boil down to the same thing. For example, people say, well, protein folding, every cell in your body solves an NP hard problem every second by just, the proteins folding into their lowest energy state, right? So, my response to that has always been, okay, great, then show me a protein that, when it folds up, then that encodes a proof of the Riemann hypothesis. Show me a protein that when it folds up, then that will let me mine bitcoins and become a billionaire, right? I mean, these things, yeah, they are amazing, phenomena in nature, but there is this enormous realm of hard instances that we know about, for example, because of cryptography, that are not being touched yet. No, and in the case of proteins, of course, there was selection pressure for them to concentrate on the easy instances, the ones that do fold reliably in one way. When that doesn't happen, we call it mad cow disease. Okay, so, within the last year, there's a guy at UC San Diego named Massimo Deventra, who's been, giving seminars all over the world about how he can solve NP-complete problems in polynomial time with something called a MEM computer. That because of some reason involving instantons just instantly gets to the lowest energy state. Okay, I mean, this is what he was claiming for some years, and then in the last few years, he actually changed the claim. He said, actually, you can simulate these MEM computers efficiently with a digital computer, it turns out. So it's actually just P equals NP. And he started not, sort of walking right up to the brink of saying that. Okay, and, this is the kind of thing, because of my blog, like every week or so, I'll get people asking me, well, what do you think about this? What do what's your reaction? I mean, my reaction is pretty simple. If NP is so easy, why aren't you rich, right? And, in the age of Bitcoin, this is a very, very easy argument to make. Okay. All right, so let me move on to the question of is NP contained in BQP? Or in other words, can quantum computers solve NP-complete problems in polynomial time? And quantum computing is the one model of computation that we have, based on known laws of physics that I think, really does challenge the extended church-Turing thesis, right? That everything, can just be simulated in BPP, right? If it were not for quantum mechanics, I think I would have believed the extended church-Turing thesis. We can come back to that question, but quantum computing, at the very least, poses an obvious challenge to that thesis. So we need to examine it. Okay. Well, first, because people have varied backgrounds, I'll have to explain what quantum computing is. Fortunately, that'll just take me one slide, for people who know complexity theory. Okay, what I always like to say is that quantum mechanics, has this undeserved reputation for being complicated or hard. It's actually remarkably simple once you take the physics out of it. Okay, so let's start with a class that we all know and love, BPP. Okay, so we can think of BPP in the following way. We have a state of our computer, which is, let's say, just a string of n bits, and we can do operations on this string, which could take bit and replace it by some function of, let's say, a few other bits. Okay, an AND gate, an OR gate, a NOT gate. Okay, but one of the operations that we're allowed to do is also a randomization operation. So we could, let's say, take the first bit and replace it by the outcome of a fair coin flip. Okay, and if we do that, then the state of our computer becomes a convex combination of two different states. In this case, 0, 0, and 1, 0. Or we would say each one has a weight or a probability of 1/2. Okay, and then we can keep going in this way, do more operations. If we do more splittings, we could get a branching tree of possibilities, right? And then at the very end, we can imagine someone looks at the computer and sees what string is there. And the probability that they see a given string X is simply the sum over all the possible paths through this tree that terminate at X of the probability of following that path, right? And the probability of following that path is just the product of all the probabilities along each of the edges. Okay, I'm belaboring the obvious because I want to, now make it quantum. Okay, but now, so this is, and then, by looking at the string X, let's say at the first bit of it, we can either accept or reject. And we put some 2/3 versus 1/3 yes or no gap. Okay, that's BPP, right? So what is BQP? All right, well, it's exactly the same thing, except, instead of probabilities annotating these edges, we're going to have complex numbers, which are called amplitudes. Okay, so for example, from the state 0, 0, we could go to 0, 0 with a 1/√2 amplitude, and to 1, 0 with, let's say, an I/√2 amplitude, right? They can be positive, negative, they can be any complex numbers of norm at most 1. Okay, and then we can keep doing operations like this. Each operation will act on only 1 or 2 of the bits at a time. But our state at any time you can think of as a linear combination, which is now a complex linear combination of over all 2 to the n-bit strings. Each one has a complex amplitude attached to it. Okay, and then at the end, we'll measure our computer, and the probability that we'll see the string X will just be this. So you'll notice it's exactly the same expression as for BPP, except that, well, this is a complex number. It wouldn't make a whole lot of sense for it to be a probability. So we'll fix that by taking its squared absolute value. right? And then we'll get a number between 0 and 1. Okay, and basically, you could ask, what linear transformations are we allowed to apply, like to get these edges? And basically, we can apply any ones we want as long as they act locally and as long as they always preserve the property that these probabilities will add up to 1. Okay, and linear transformations that do that are what we call unitary transformations, right? They're just ones that preserve the 2 norm. Okay, so the entire hope, oh yeah, I forgot, but the real conceptual difference with quantum computing is that you put these things around each string, okay? Okay, yeah. Well, yeah. That's right. So that's why I just said it has to be unitary transformations that generate the. So you can do any unitary transformation, which I basically just defined the class by saying you can do any linear transformation that necessarily does preserve this. So I just defined the problem away for you. Okay. Good. So so the entire hope of getting a speed up from a quantum computer is to exploit the way that these amplitudes work differently than classical probabilities do. Okay, so when I calculate the probability of some string, right, I just have to add up probability from each path. These are all non-negative reals, and I just tot them all up. Okay, but when I calculate the amplitude for a string, I'm adding up all these complex numbers, and they can cancel each other out, right? So if an event could happen one way by a path with positive amplitude, and another way by a path with negative amplitude, then they can, as we say, interfere destructively and cancel each other out, with the result being that that string will now have probability 0. Okay, and whereas even though if I had blocked either one of the paths, then that string would have non-zero probability. Okay, so that's quantum interference, and that, in some sense, is what everything boils down to, right? The goal with any quantum algorithm is to choreograph a pattern of interference so that for each wrong answer, you get destructive interference between, the different paths leading to it, whereas for the right answer, you get constructive interference, and all the paths leading to that have amplitudes that are pointing in more or less the same direction. And you've got to do that efficiently, and you've got to do it despite not knowing in advance which answer is the right one. That's all. Okay, so now I should address what I think of as the fundamental misconception about quantum computing. In other words, the misconception that has infected almost every popular article that has ever appeared about this subject in the last 25 years. Okay, which is what what almost every single person wants to say is, well, a quantum computer is just a computer that can try every possible answer in parallel, right? Or, it can just work on each answer in a different parallel universe. Okay, so that, for example, Shor's algorithm would work by just trying each divisor, in another universe. Okay, and my response, is always, well, if it were that simple, why would you have needed Peter Shor to think of it? But more seriously, let's understand what goes wrong with that. I mean, yes, with a quantum computer, you can very easily create an equal superposition over all possible answers, let's say to your NP-complete problem, even if there were exponentially many of them. Okay, that's trivial to do. The trouble is, for a computer to be useful, at some point you've got to look at it. Okay, and if I just took an equal superposition over all answers and measured it, and not having done anything else, all I'm going to see will be a random answer, uniformly random, right? Just by the rule that I wrote on the last slide. And, well, if you just wanted a random answer, you could have picked one yourself with a lot less trouble. Okay, so so the entire question is, how do you get a large probability of observing the answer that you want? And that, in turn, boils down to, how do I concentrate a large amplitude on the answer that I want? And that is a question about interference, okay, of amplitudes. So it's going to be a global phenomenon that's going to involve, this entire vector of size 2 to the n, and not just one little component of the vector saying, hey, everyone, look over here, I found it. I found the satisfying assignment. Okay, so it's much more subtle than that. And, for some special problems like factoring, we do know how to choreograph this interference pattern that actually concentrates the amplitude on what you want. Okay, but what about for NP-complete problems? That's the obvious question. Okay, well, so people studied this already in the mid-90s, and there's nearly as famous as Shor's factoring algorithm is another quantum algorithm called Grover's search algorithm. Okay, and this is the algorithm that can take any list of n possible solutions. You know, it could be for a combinatorial search problem, could be just n elements in an actual physical database, and it can search for a desired solution, you know, one that that matches given criteria in only about square root of n steps rather than n steps. Okay, so it's a quadratic speed up, and you know, it's a beautiful algorithm. It basically involves starting out with an equal superposition over all the possible answers, but then you don't just measure it immediately, which would be the naive thing, right? Instead, what you do is you repeatedly apply linear transformations that concentrate more and more amplitude on the right answer. So initially, you have a 1 over square root of n amplitude on the right answer, let's say, which means 1 over n probability if I were to measure right now, right? Useless. Okay, but then I do what's called the Grover diffusion step, which makes the amplitudes evolve like this. I hope you appreciate my PowerPointing from this morning, okay? You know, and then what this will do is it will make like 3 over square root of n amplitude go on the marked item. If I do it a second time, I'll get 5 over square root of n amplitude on the marked item, and then 7 over square root of n, and so forth. So each time I'm getting like order 1 over root n more amplitude, and that means that after only about root n steps, I've got a constant fraction of all my amplitude on the marked item, and now I can measure and I'll see it. So in some sense, the square root speed up is directly coming from the fact that, you know, we can add amplitude instead of just adding probabilities, right? It's coming from the Pythagorean theorem, if you like. Okay, but we also, you know, in fact, even before Grover's algorithm was discovered, it was proven to be optimal. Okay, in a beautiful result by Bennett, Bernstein, Broussard, and Vazirani. And what they showed is that if you don't exploit any additional structure in your problem, then Grover's algorithm is the best that you could do even with a quantum computer. Okay, so for black box searching, even a quantum computer needs order square root of n steps. And as a corollary of that, they deduced that there is an oracle relative to which NP is not in BQP. In fact, relative to a random oracle, NP is not in BQP. Okay, so you know, in other words, if there is a fast quantum algorithm for NP-complete problems, of course we don't know if there is. We don't even know if there's a classical algorithm. Okay, but if there is, then it has to exploit structure. Let me mention some other things around the BBBV theorem. In 2004, I was able to extend it to show that relative to an oracle, we even have NP is not efficiently solvable by a quantum computer with quantum advice. Okay, so with a polynomial size quantum advice state that it gets, you know, which could be a superposition encoding exponentially many bits of information. But then again, you have to measure it somehow, and you only see a limited amount when you measure it. Okay, so I showed there's an oracle relative to which NP is not even in BQP/Q poly. Okay, on the other hand, in the interest of honesty, I should tell you that just a couple months ago, I managed to construct an oracle relative to which NP is in BQP, but the polynomial hierarchy is infinite. Okay, so, you know, who cares? What's this telling you? Well, you know, this is affirming that yes, BQP is a different kind of animal from BPP, for example, right? If NP is in BPP, then, you know, undergraduate exercise, then the polynomial hierarchy collapses, and that's by a completely relativizing proof. Okay, but, you know, NP, you know, being in BQP, if that has such a terrible consequence, then the proof would have to not relativize. And in order to prove this, I built on this recent beautiful breakthrough by Ron Raz and Avishai Tal, where solving a problem that was open for 25 years and that many of us had worked on, they managed to construct an oracle relative to which BQP is not in the polynomial hierarchy. They used a problem that I had proposed, and that I proved in BQP, but the part that the one part I couldn't do was this part. Show it not in PH. Okay. Okay, but let's move beyond the black box setting. Could there be an efficient quantum algorithm to solve NP-complete problems that would exploit their structure? Okay, well, a lot of people have hoped so. Have even invested a lot of money in quantum computing, startups in the hope or belief that the answer is yes. A lot of these hopes for the last 20 years have centered around something called the adiabatic algorithm, which was proposed by Ed Farhi and his collaborators around 2000. And this is, you can think of it as just a quantum analog of simulated annealing. Okay, so it's a heuristic optimization method where you sort of start out by applying a Hamiltonian, which is just the like a thing that the instantaneous time version of a unitary transformation that has like a known and easily prepared ground state. The ground state is like the lowest energy state of the Hamiltonian, where it would like to just, the state would like to just sit there doing nothing as you apply the Hamiltonian. Okay, but then what you do is you slowly vary the Hamiltonian until you end up with a different Hamiltonian, let's say H sub f, whose ground state encodes the solution to an NP-complete problem that you care about. And it's very easy to construct such a Hamiltonian. All you have to do is say, like, let's say given a 3-sat instance, well then for each clause that's violated, I'm going to create an energy penalty, right? And that the state with the lowest energy will be the state that satisfies the largest number of clauses, right? And that's a standard transformation. Okay, and then there's this result from the 1920s called the adiabatic theorem, which says that as long as you vary Hamiltonians slowly enough from one to the other, then you start in the ground state of one, you will end up in the ground state of the other. Okay, so this says that, okay, we will end up in the ground state of HF, thereby solving our NP-complete problem. The only question is how slowly do we have to vary it? They said this looks really promising, and they had a paper in Science, and they had some empirical data. It looks like this is solving 3-sat in polynomial time. Or instances up to size 20 or something. And then some of us in CS were skeptical, and Farhi was like, well, if the graph had been had looked exponential, would you say it's going to turn and become polynomial? You're just ideologues, right? You just you think things are going to become exponential just because that's your prior. It turns out that people then analyzed it, and the running time of the adiabatic algorithm depends crucially on a quantity called the minimum spectral gap of the Hamiltonian, which is just the gap between the smallest and the second smallest eigenvalues as you vary it. Okay, so basically you need to use time that scales like the inverse of this gap, right? Which means the only way you would need exponential time would be if these two eigenvalues somehow got exponentially close without touching each other, and then again moved apart, right? That sounds pretty absurd, right? Yeah.
It depends on the spectral gap of the final state.
It depends on the minimum spectral gap as you vary the Hamiltonian. Yeah, but why should they ever have to get exponentially close, right? It looks silly in the picture. Okay, but then people managed to analyze it and prove that for various hard instances of 3-sat. For that matter, even instances of 2-sat, lo and behold, this gap does become exponentially small. Okay, Farhi told me a wonderful story about it, which is that he went to experts in condensed matter physics because they have like decades of experience calculating these spectral gaps for their own reasons. And he asked, well, based on all your experience in our system, do you think that our gap is going to shrink polynomially or exponentially the number of particles? And that was a weird question, but the guy thought about it and he said, I think it's going to increase exponentially. Now, that was not the answer that Farhi wanted to hear. So he said, why? What's the physical reason for it? And the guy thought some more, and he said, well, it's because otherwise your algorithm would work. Okay. All right. We'll come back to that point about, can you go the opposite direction and just assume NP is hard and use it to infer something about physics? Okay. But in any case, we've now learned some more about the performance of this adiabatic algorithm and related quantum optimization methods. We've learned that there are types of fitness landscapes where the adiabatic algorithm will reach the global minimum in polynomial time, even though classical simulated annealing would take exponential time. Okay, so they're beautiful examples. They look kind of like this. They've got like a wide basin with a big, nice global minimum here, but then there's a spike kind of blocking the way to it. Okay, and classical, depending on the height and the width of the spike, you can make it so that classical simulated annealing will get stuck over here for an exponentially long time, but the quantum adiabatic algorithm will just go right past it and just, like not barely even notice it and just go right down there. This is because of the phenomenon that the physicists call tunneling. If you've ever heard of quantum tunneling, this is that. Okay? But they also found, well, you can construct other fitness landscapes where simulated annealing reaches the global minimum in polynomial time, but the quantum adiabatic algorithm needs exponential time. Ones like this, where, you've got a big plateau here, that you need to somehow get across. And then, of course, there are landscapes where both of them need exponential time. Okay, although, of course, this leaves the question, could other algorithms do better? Okay, and it also leaves the question, well, what about in practice? We're not going to, I think, fully understand the performance of these quantum heuristic algorithms in practice until we have the actual hardware to test them out on. Because you can do simulations on classical computers, but then you can only go up to about 40 qubits and you're done. Okay, which brings me to the next question. Well, is BQP realizable in our world? A lot of people ask that for some reason. Well, I'm not going to tell you the answer, okay? I'm not going to, be a fanatic and, because obviously we won't know for sure until we, build the systems and see what happens. But I do insist that, the answer, yes, you can build a quantum computer in principle. It's all just, 1920s physics. It's all completely, established physics. The quantum fault tolerance theorem says in principle you can correct errors. And, it is, yes, it took more than 100 years to go from Charles Babbage till the invention of the transistor. And maybe, in this case too, who knows how long it'll take. It could be another 100 years, but yeah, sure, in principle it's possible. That is the conservative view. Okay? The view that there is some deep obstruction that you could never do it, that is the radical view. Okay? That's the view that would require a revolution in physics. Okay, so, I tend to be conservative. That's all I can say. But hopefully we will learn more soon. So some of you may know that there's, enormous efforts underway right now all over the world. Google, IBM, IonQ, to build these devices, and some billions of dollars are being invested in it. Okay, Google in particular is right now building a 72 qubit chip, which they call bristlecone. They're hoping to demo it by this summer. Although we don't know whether it will be able to do something classically hard yet, because it all depends on the quality of the qubits. Okay, but they have a 20 qubit system that works pretty well. It's an enormous engineering problem to scale it up and get it all working together. But what they're hoping, 70 qubits are probably, they might or might not be useful yet for anything whatsoever. Okay, but what many of us are hoping is that they will be just enough to do something that is useless but hard. Okay, useless but hard for a classical computer to simulate. This is a goal that's been given the unfortunate name of quantum supremacy. Okay, and but this will obviously be a major milestone, in sort of answering the people who think that this can't be done. And so, the near-term goal for Google and some of the others is just to sample from probability distributions, let's say over 70-bit strings or something, that that in the asymptotic limit, if these same distributions could be efficiently sampled with a classical computer, then you would get collapses like p to the sharp p would equal bpp to the np, and hence the polynomial hierarchy would collapse. Okay, this comes from theoretical work that I and others did about a decade ago. Now, it's not quite as nice as that because, of course, Google or anyone in real life will only be able to very, very approximately sample from these distributions. We don't yet know whether approximate sampling would have such a dramatic complexity consequence. But at any rate, it seems classically hard, right? We will put that out as a question. By the way, you might wonder, well, like if you're collapsing these classes, right? I mean, doesn't it take the power of NP to just get from this class to this one? And doesn't that mean that this sampling device is sort of solving an NP-complete problem? Well, I don't think so. I don't think really, right? Because, it's that would be true only if you had a classical simulation of the device, right? That doesn't really follow, but, just because you have the device itself. Right. Okay. Anyway, all right. Let me now move on to the last and most fun of my questions. Is there anything beyond BQP? Okay. How could we even exceed what a quantum computer could do if we suppose that not even they will let us efficiently solve NP-complete problems? All right. Well, there's a bunch of ideas. The first one is the relativity computer. Right? Why only quantum computers? Okay? So, the idea is simple. You start your computer working on your NP-hard problem. You board a spaceship. You accelerate to relativistic speed. You decelerate. You return to Earth. Billions of years have passed in Earth's reference frame. Civilization has collapsed. If it didn't collapse in 2020 or so, all your friends are long dead. Okay, but if you can dig your computer out of the rubble and it's still connected to a power source somehow, well, then you can read the answer to your hard problem. I mean, this raises an obvious question. Why doesn't anyone try it? I mean, if you're worried about your friends, then just bring them on the spaceship with you, right? There actually is an interesting physics answer to that question. I think, and I think it has to do with, well, how much energy would it take to, if you wanted an exponential computational speed up, then you can calculate that you would actually have to accelerate exponentially close to the speed of light. Okay, but to do that, according to special relativity, that takes an exponential amount of energy. So now we have to think about, well, are you spending 2 to the n time just to fuel up your spaceship before liftoff? And issues like that. Okay, a related idea is what I'll call the Zeno computer. Okay, this is a computer that does its first step in 1 second, the second step in half a second, the third step in a quarter second, an eighth second, and so on. So after 2 seconds, you've done infinitely many steps, right? Surely that would give us, NP-complete problems and much more. Okay, so why doesn't anyone try that? Well, people sort of do, right? People try to overclock their microprocessor, right? But some of you know the danger. If you run your microprocessor too fast, it will melt. That's why your computer has a fan. Okay, but you can calculate if you wanted to safely run a microprocessor faster and faster. Again, the limiting factor is sort of energy, right? Energy for cooling, but also just the energy that's inherent in the computation itself. And what you can, based on the known laws of physics, you seem to reach a fundamental limit, if not before, then certainly when you would be doing 1 computation step per Planck time, okay, which is 10 to the 43 steps per second. Okay, and why do you reach a limit there? Well, basically just because in order to run a computer that fast, you would need so much energy that it would exceed its own Schwarzschild radius, which is a fancy way of saying that your computer then collapses to a black hole. Sorry. And apparently that's what a black hole looks like, as we now know. Okay, so I love that as nature's way of telling you not to try something. Okay. All Okay, but then what about non-relativistic quantum mechanics wasn't the last word in physics, right? Today physicists think in terms of quantum field theories. Okay, could they let you somehow get beyond BQP? And like my intuition, would have been, well, probably not, because they're still just quantum mechanics. They're just like a fancy application program, running on the quantum mechanical OS. Okay, but, quantum field theories are really, really complicated, even to just define them and get out sensible and finite answers. Okay, so it took a long time for people to even properly formalize this question and treat it. And the end result, as of now, seems to be, yes, indeed, quantum field theories can be efficiently simulated with a standard quantum computer, that is in BQP, to whatever extent the quantum field theories are well defined in the first place. Okay, so there's a beautiful work by Jordan, Lee, and Preskill from a few years ago that shows this for some non-trivial, interacting quantum field theories. Has not yet been extended to the full standard model of elementary particles. There are some technical issues in doing that, but that would be a great next step. There's also earlier work by Friedman, Kataev, and Wang that looked at topological quantum field theories, which are particularly simple quantum field theories. And they were able to show, using work of Witten from the 1980s, that yes, in the end of the day, these give you the same power as ordinary quantum computers. These also give you BQP. Okay, what about quantum gravity? Okay, well, we don't yet have a quantum theory of gravity. So you're sort of, we're sort of free to project any of our hopes or dreams onto it, right? Maybe that would let us solve NP-complete problems. Who knows? But, in the last 20 years, some of you may know, there was a sort of, maybe the most important thing to come out of string theory was this thing called the ADS-CFT correspondence. ADS meaning anti-de Sitter space, meaning, universes with a hyperbolic space with a negative cosmological constant. Ours has a positive constant, but, so these are kind of toy universes. But, it turns out that these, you can have a quantum gravity theory in these ADS spaces, which is completely equivalent to what's called a CFT, a conformal field theory, which is just like a totally ordinary quantum field theory with no gravity, and which is defined on the boundary of the space-time. So there's like a holographic mapping between this bulk, quantum gravity theory and the boundary field theory. Okay, now this strongly suggests, although it doesn't prove, that if you believe this ADS-CFT stuff is indicative of the real world, then even gravity can be encompassed, within the umbrella of standard quantum mechanics, which would in turn suggest that even quantum gravity could be efficiently simulated in BQP. It doesn't prove that. Okay, and I think it's a wonderful challenge for the people in this field. Do a rigorous analysis that shows that at least if you believe ADS-CFT, then within this model, of quantum gravity, that say the Church-Turing thesis holds, or that everything can be simulated in BQP or whatever. Okay. Okay, and then there's 5 minutes. Thanks. Okay, then there's the question, well, if you want to solve an NP-complete problem, why not just exploit cosmology? Why not just spawn off an exponential number of baby universes and have each one work on another candidate solution? Well, in certain types of space-time geometries, that would actually work, it seems. Okay, but unfortunately, it appears that does not work in our space-time geometry. Okay, and in particular, as you may have heard, 20 years ago, it was discovered that space is expanding at an exponential rate. Okay, that's called the vacuum energy, or also called the dark energy, or the Einstein's cosmological constant. That was the biggest empirical discovery in physics of the last several decades. Okay, but one, it has an enormous consequence for computation, which is if you believe in, that this cosmological constant will really just stay constant, and if you also believe in what's called the Bekenstein bound, which is that thing that says you can only store so many bits or do so many steps within a given region of space-time before that region collapses to a black hole, and you put that thing together, well, there's only a finite region of space that we can ever access. in a universe with a positive cosmological constant, right? Because galaxies that are sufficiently far away from us are receding from us faster than light. Okay, so there's only so big a computer that you could ever build, let's say 20 billion light years across or something like that, before the faraway parts of the computer will be receding from you faster than light, and you can no longer receive a signal from them. Okay, and this would put, again, assuming the Bekenstein bound, this would put an upper bound of about 10 to the 122 on the number of qubits that you could ever have in any quantum computation, in our world, where you get an answer out at the end. So, one interpretation of that would be, well, everything is O of 1, so complexity theory is finished, and we should all go home. I think that, 10 to the 122, is a constant, but come on, it's a big constant. Okay, but, this exponential spawning thing, it says, is not going to work. Okay, there was a beautiful observation by Abrams and Lloyd 20 years ago. So now we're going to get into hypothetical modifications of the known laws of physics. If none of the stuff we know lets us solve NP-complete problems, then what about making stuff up, right? So Abrams and Lloyd said, well, if there were, quantum mechanics is this completely linear theory, right? A striking feature of it. But if you added just the tiniest nonlinearity to the Schrodinger equation, quantum mechanics, which my UT Austin colleague Steven Weinberg has been speculating about for decades, or people have searched for, haven't found it. But if that existed, then what you could do is you could have two states that are exponentially close. One corresponds to no solutions to your NP-complete problem. The other corresponds to one solution. And then with a nonlinear evolution, you could kind of pry these apart until they're orthogonal. And you could, in fact, solve NP-complete problems in polynomial time in that kind of universe. In that kind of universe, you could also send signals faster than light. So you could do a lot of fun stuff. Okay? Maybe this is just additional indication that, Schrodinger equation is linear. What about the time travel computer? Very simple idea. You receive a string X from the past. You check it. Check, does it satisfy your Boolean formula? If it does, then send the same string back to the past. If it doesn't, then send the lexicographically next string back to the past, looping back to the first string after you've reached the last. Okay? Now, the only, assuming that phi is satisfiable, the only way for nature to avoid a grandfather paradox, to avoid a paradox of causality, will be for it to just give you a string that is satisfiable. Woohoo! All right. Well, so you can even, work out what is exactly the power of this model of computation. John Watrous and I had a paper about this a decade ago, not the paper I based my tenure on, but where we showed that, with a closed time-like curve, you could do exactly the problems in p-space. Okay, so it's even more than NP. And this is actually true whether it's a classical or a quantum computer in the closed time-like curve. It's all just p-space. Okay, that was, we had fun proving that theorem. Okay, but, closed time-like curves, as I hardly need to mention, would break many principles of physics. The second law, quantum mechanics, a lot would go out the window. So maybe this is just additional indication that there are no closed time-like curves in our world. Yakira Haranov believes that the universe has a post-selected final state. So there's not just a special Big Bang, there's like a special state at the end of time. And then you could say, well, if that special state of, some bit has to be 0 at the end of time, then what if I just guess a random solution to my NP-complete problem? And if it's not satisfying, then I take that bit and I flip it to 1. And now nature, in order to satisfy its teleological final condition, will have to give me a solution. All right, well, you can think about such things. You could define a complexity class around them. I did that. With a quantum computer, you get, again, even more than NP. I don't believe our universe has a post-selected final state. I don't know about you. You can look at, what if you could make multiple non-collapsing measurements of a quantum state? Okay, this is a model that I studied years ago, and then in more recent work, we looked at it again. So in this model, you could very easily find collisions, let's say, in a 2-to-1 function. To do that, I would just have to make an equal superposition over all my inputs x, compute my function f in superposition, then measure this f, and then what I'm going to be left with in this x part is just an equal superposition over the two pre-images of the f of x that I saw, right? Call them x and y. I'll have an equal superposition like this. Now, if only I could take this state and measure it twice, then I would get both pre-images, right? And I would have found a collision in my hash function. Okay, quantum mechanics, alas, doesn't let me do that. But you could study what would happen in a world where you could do it. So we did. And what we showed is that in that world, you could efficiently solve all problems in statistical zero knowledge, including graph isomorphism, including approximate shortest lattice vectors. Okay, so, that's pretty cool. But even in that world, in the black box setting, you still couldn't do NP-complete problems. Okay, so I love that nature, there are ways to get a little bit more, but, and not all the way to NP. All right, so let me conclude with the thought, do we live in a bounded universe where, there are just these impossibility principles, no perpetual motion machines, no faster than light signals, no NP super search. And like in the first two cases, physicists would say, yeah, these are basic principles by means of which we can explain other things, right? And should we do the same with this no super search principle? I would lean towards saying yes. And my final thought, did anyone foresee in 1971 that NP completeness, as a concept, would have this kind of reach into, questions about black holes, cosmology? I don't actually know. I wouldn't be born for another decade. But let me end there. Thanks.
So we've got some questions. We've got somebody very eager. So
very eager. So first of all, let me say I never thought I'd hear such an entertaining talk on physics. So thank you, Scott. It was great. I really enjoyed it. So I'm curious. So Steve Cook wrote this 12-page thing on NP. Yours is 122 pages. What took you 122 pages to say?
Yeah. Well, you can read it, but mostly, I tried to summarize all the progress that there has been on circuit lower bounds, algebraic lower bounds, the Momoli-Sahoni GCT program, permanent versus determinant, yeah, and then it just kept getting longer and longer, because I didn't want to just, you can take the path that Mike Zipser took yesterday, just saying, look, there's nothing that's obviously progress, right? Or you could take the path saying, well, there's all this stuff that might be progress.
I see.
Yeah.
Good, thanks.
Yeah.
I think there are a number of questions here.
Hi. Great talk, really.
Thanks.
Always when I hear you. There is some kind of dichotomy here. When you want to say optimistic things, positive things, you say, oh, Google is building this chip that will be able to handle 70 qubits, and it will be indication that maybe. And when you talk about the negative stuff, negative evidence, you talk about asymptotic negativity. So, how can you comprise those two things? That 70 qubits will give me optimistic indication, but the pessimistic indication is as n goes to infinity.
Well, there's always a gap between asymptotic statements and, the results of experiments that we can do in finite time, right? That has been, a thorn in the side of complexity theory from the very beginning, right? And will always be a thorn in our sides, right? But let's suppose that with 70 qubits, you could do, you could solve a problem, in 10 microseconds, sample from a distribution where after a lot of thought, the best that people can do is using a Hadoop cluster or using some, classical computing cluster, they can do it in, a few days, right? Or a few hours, right? Now, does that prove that, our universe has power beyond P? No, of course it doesn't prove it. But I would say, it puts the ball more firmly in Leonid Levin's court and, Oded Goldreich's court, right? Or in Gil Kalai's court, right? Articulate, okay, so then, if 70 doesn't satisfy you, then what number will, right? Like there could be people where even once a quantum computer is built with 100 million qubits, let's say, and in fact, completely breaks RSA, they'll say, okay, well, God was cruel to us with the constant factors, but, it's still all just, right, but, at that point, the extended church Turing thesis has been completely emptied of its empirical content. Right. I think it just becomes silly at that point. So, you do what you can, basically.
Okay, so I know we've got a question at the front. And were there other questions at the back? I thought there were a couple more. No? Okay.
No microphone needed.
Yes, but still.
All right.
Is there any evidence of a computing Manhattan project?
You mean of a Manhattan project to build a quantum computer?
Or any other stuff kept secret from us?
Well, I mean, here's what I'm still amazed at the Manhattan Project itself, that they actually managed to keep it secret, right? I feel like if someone tried to do a Manhattan Project today, then like within 10 minutes, it would be on Twitter, like, hashtag uranium, hashtag, right? I mean, like how would you do such a thing, right? So, I mean, in quantum computing in particular, right? Like, it's a community of, let's say a few thousand people. Right? But it's like, you would notice if they were all getting vacuumed up into some secret project, right? And we just haven't seen it. I mean, yes, the intelligence agencies are interested. A lot of governments are interested. Yes, there are companies that are now doing things that they're no longer always publishing, right? And, the details of their architecture, right? Sometimes they now treat as trade secrets. The idea that like, the NSA is like, 30 years ahead of the rest of the world with some dark project. If that's true, then I think that they're also running this gigantic cover operation, right? To the point where it becomes, unfalsifiable. We might as well, talk about, that they also killed JFK or whatever. You can't. See, that's exactly what I'm saying. You can't.
So one last call for questions. We'll see if, okay.
Scott, can you say just a few words about the Gil claims?
Yeah, they're wrong. No. Okay. So Gil, believes that quantum computing can never scale for some deep reasons, but those reasons are, he himself admits are yet to be discovered. Okay. He's repeatedly put forward, like hypothetical models of like, here is what the noise could look like in such a way that, the fault tolerance theorem would fail and you wouldn't be able to do scalable quantum computation. Now, one problem is that his models of noise tend to involve teleology. That is like, assume that, nature knows what gates you're going to apply in the future. And then, they can adversarially pick the noise, right? And once you have noise like that, it's very hard to kill quantum computation without also killing classical computation, right? Like if your noise model would also prove that scalable classical computing is impossible, then it's proven too much at that point, right? But then, often, the answer is like, we don't know. Like even with Gil's kind of, I would say, physically completely unmotivated noise models, often like, it is not known, whether, maybe quantum computation can survive, even against those. Or, if not all of quantum computation, then at least quantum NC1, which would be enough to do Shor's algorithm, which would, but what I do, what I really respect about Gil is that, from his skepticism of quantum computing, he draws the conclusion that, gosh, everybody should be working on this because, when we really discover why it's not possible, that's going to be a revolution in physics, right? He's absolutely correct. But for some reason, none of the other skeptics draw that inference, right? Right? I don't understand why not, right? But Gil, he puts his money where his mouth is. I mean, he's a founding member, leader of the Quantum Computing Center at Hebrew University, right? And and he says that he might be wrong, and he would love, he'd be very happy to be proven wrong. So I think we will try to make him happy.